What is up, engine heads? Today we'll be doing a detailed comparison of three different kinds of gasoline fuel injection systems: port fuel injection, direct injection, and dual injection. We'll see how each system works and we'll see how they differ from each other. And of course, we're going to examine the benefits and drawbacks of each setup. So let's get started. So both port and direct injection essentially do the same thing. As the name implies, they inject fuel so that the fuel can mix with the air and create a combustible air-fuel mixture, which when combusted creates combustion pressures which drive the piston downward, which spins the crankshaft, which then ultimately turns the wheels of the vehicle. Now, they may do the same thing, but port and direct injection differ in the location of where they inject the fuel. As the name again implies, port fuel injection injects the fuel into the intake port of the engine before the intake valve, whereas direct fuel injection injects the fuel directly into the combustion chamber after the intake valve. This means that in the case of port injection, you're usually going to find the injectors somewhere on the intake manifold of the engine, while in the case of direct injection, the injectors are going to be either on the valve cover, or if they're not there, you're going to find them underneath the intake manifold, protruding directly into the cylinder head. Although the location of fuel injection may seem as something trivial, in reality it plays a fundamental role in the design of the engine and noticeably influences performance, efficiency, emissions, and maintenance concerns. Now, both systems, port and direct injection, consist of essentially the same parts: a fuel tank or fuel reservoir, a fuel pump, some fuel lines, and fuel injectors. Now, the engine control unit, or the ECU, measures the amount of air coming into the engine using various sensors, and then tells the injectors how much fuel to inject so that the amount of fuel injected corresponds to the amount of air entering the engine, all with the goal of creating combustion that is as close to ideal as possible. But direct injection has a more challenging task than port injection. Because fuel is injected directly into the combustion chamber, the direct injectors must spray the fuel with sufficient force to overcome the pressures generated by the engine's compression. And if you have ever compression tested an engine, you know that the upward movement of the piston inside the engine can easily generate pressures in excess of 100 psi. Now, port injectors don't have to combat this compression pressure because they're injecting fuel before the intake valve, which means that they're injecting either into atmosphere if they start injection before the intake valve opens, or they're injecting into a vacuum if they start injecting after the intake valve opens. This means that port injection needs somewhere between 40 to 65 psi to operate properly. This is obviously less than the compression pressures generated by the engine itself, which means that if you try to use a port injector to inject fuel directly into the combustion chamber, the fuel would actually never leave the injector. This is why, to ensure that it can easily overcome the pressures generated by the engine's compression, direct fuel injection usually operates at fuel pressures upwards of 2000 psi, that's 140 bars, which is 140 times the pressure of Earth's atmosphere, and it's also 20 times the pressure of the engine's compression. But of course, to generate such high pressures, direct injection needs additional parts. First of all, it can't work with a simple one fuel pump setup like port injection. Instead, it needs two fuel pumps. The first one is an in-tank low-pressure fuel pump, which sends fuel down the lines from the tank to a camshaft-driven high-pressure fuel pump, which ramps up the pressure to the required amount and then sends it into a fuel rail from where it gets distributed to the injectors. The injectors themselves are also radically different to port injectors. They're more advanced because they need to be capable of rapidly opening and closing against very high fuel pressures, and also because their tips are located directly inside the combustion chamber, they must be capable of operating properly while being exposed to the extremely harsh conditions created by the engine's combustion. Port injectors, of course, don't have any of these concerns, which is why in general they're much less expensive and far less complex than direct injectors. In general, a direct injection system, because of the increased complexity and increased number of parts, increases production costs and vehicle prices. So as we have seen, the location of the injection determines the pressure at which the system needs to operate, and it also drives up the number and complexity of parts. But if you have paid attention, you might have also noticed that the location of the injection also determines the timing of the injection. As we have said, port injectors inject either into vacuum or into atmospheric pressure if injection starts before the intake valve opens. And when does the intake valve open? Of course, during the intake stroke of the engine. And this tells us that port injection occurs during the intake stroke. In fact, it can occur during any other time, during any other stroke of the engine, but the fuel actually gets into the chamber during the intake stroke. When it comes to direct injection, you may recall that it has to face the compression pressures of the engine. And when does the engine generate compression pressure? Of course, during the compression stroke. And this tells us that direct injection occurs during the compression stroke of the engine. In fact, in most modern, more recent systems, direct injection occurs during the later stages of the compression stroke, right before combustion occurs. And although in some older systems, a direct injection would occur at early stages of the compression stroke or even earlier during the intake stroke, depending on the engine speed and engine load, in general, direct injection starts much later and is of much shorter duration than port fuel injection. So how does the timing of the injection affect the engine? Well, for one, it enables a higher compression ratios in the case of direct injection. Now, don't be confused. Compression pressure is the pressure generated by the upward movement of the piston inside the engine. But the compression ratio is the ratio between the largest and the smallest cylinder volume of the engine. The higher the compression ratio, the more we compress the air-fuel mixture inside a cylinder. The more we compress it, the closer we bring the piston to the heart of the combustion. And the closer the piston to the combustion, the more of the combustion's energy can be transferred onto the piston and turned into motion. In other words, a higher compression ratio can lead both to better performance and higher efficiency. So how exactly does different injection timing enable a higher compression ratio? Well, to understand that, we need to observe port and direct injection side by side. And as you can see, in the case of port injection, the fuel enters the cylinder much earlier and spends more time in the cylinder than in the case of direct injection, where the fuel enters only at the late stage of the compression stroke. Now, you have to remember that the insides of an engine are hot. Temperatures inside the cylinder are always high because combustion occurred there just a few milliseconds ago. The intake valves also carry a lot of heat because they're constantly exposed to the heat of the combustion. And the air-fuel mixture coming inside the cylinder of a port-injected engine has to pass right along the intake valve, and it's picking up heat from the valve as it does so. And all of this heat inside the engine means that the more time the air-fuel mixture spends inside the engine, the hotter it gets. And the hotter it gets, the greater the chances of its spontaneous combustion, or NOC. Now, NOC is spontaneous abnormal combustion of the air-fuel mixture that occurs after the spark plug has fired, and it occurs outside the evenly propagating flame front initiated by the spark plug. Now, for the air-fuel mix to spontaneously self-ignite, it needs heat. And it needs a lot of heat. And this heat can come from two main sources. The first source is the compression of the air-fuel mixture itself. The more we compress a gas, the closer we bring its molecules together, causing them to bump against each other more, increasing their friction and thus the heat of the gas. Now, the air-fuel mixture is of course also a gas, which means that the more we compress it, the higher the compression ratio, the greater the heat of the air-fuel mixture, and the greater the chance of its spontaneous self-ignition. Now, the second source of the heat comes from the combustion itself. When the spark plug fires, it initiates a flame front which spreads evenly outward from the spark plug. Of course, this flame front exerts heat and pressure on the uncombusted air-fuel mixture outside of this flame front. And if the uncombusted air-fuel mixture is already hot enough from the compression, then the added heat and pressure from the combustion can cause it to ignite spontaneously, leading to NOC. And if NOC persists long enough and if it's strong enough, it will destroy the engine. Now, as we said, the air-fuel mixture spends more time inside a port-injected engine than it does in a direct injection engine, which means that it picks up more heat and it's already at a higher temperature when combustion starts. Now, when we add the heat of compression and the heat of combustion onto the already higher base heat of the air-fuel mix inside a port-injected engine, it means that we can enter NOC territory more easily, and the result is that we have to be somewhat conservative with the compression ratio inside a port-injected engine to prevent NOC. Now, in the case of direct injection, as we said, the fuel enters the system later at a late stage of compression, which means that the air-fuel mixture spends less time inside the cylinder picking up heat, which results in a lower base heat once combustion starts. And because of this, we have more room to increase the compression ratio of the engine in a direct injection setup. And as we said, a higher compression ratio can lead to better power and more efficiency. And this is one of the key reasons why so much research and development has been invested into direct injection. The other key benefit of direct injection is that it can reduce fuel consumption and harmful emissions. It can do this because it sprays fuel directly into the combustion chamber, which means that the fuel sprayed by the injectors is the same amount of fuel that actually ends up in the combustion chamber and can be combusted. But this is not the case with port injection. Because fuel is injected outside the combustion chamber, the amount of fuel released by the injectors is not necessarily the same amount of fuel that ends up in the combustion chamber. Some of the fuel may end up as droplets that accumulate on the walls of the intake manifold or the intake ports of the cylinder head. Also, the intake valve might close before all the air-fuel mix enters the cylinder. And the result is that the difference between fuel injected and fuel combusted is greater in port-injected engines, resulting in less accuracy and less control over the injection process, which can negatively impact emissions and fuel economy. But there are two sides to every coin, and what may seem as drawbacks of port injection can also be its benefits in different scenarios. As we said, the air-fuel mixture spends more time inside the cylinder of a port-injected engine, and although this allows it to pick up more heat and ultimately limits the compression ratio, it also gives the fuel more time to vaporize and mix with the air. To achieve good combustion, you want to burn all the fuel inside the cylinder. And to do that, you want the air-fuel mixture to be as homogeneous as possible. In other words, you want the air and fuel well mixed together. And one way of doing that is tumbling the air-fuel mixture as much as possible. Now, there's plenty of time for tumbling the air-fuel mix inside a port-injected engine. It first occurs when the air and fuel enter the cylinder together and swirl around. And then it occurs some more during the entire compression stroke when the piston rapidly pushes the air-fuel mixture upward. But unfortunately, direct injection doesn't have nearly the same amount of time available to vaporize the fuel. As we said, most recent setups start injecting only in the second half of the compression stroke. Now, direct injection makes up for this by having extremely high fuel pressures, which dramatically improve fuel atomization, and also it uses tricks like cavities, special cavities in pistons, against which fuel is sprayed and against which the air-fuel mixture tumbles and swirls. But despite this, direct injection can suffer from poor air-fuel mixture homogenization at low engine speeds. At low RPMs, the piston speeds are also lower, which means that the piston pushes against the air-fuel mixture more slowly, causing it to tumble less, which means that at low RPMs, direct injection engines can experience little pockets of unburned fuel within the air-fuel mixture. This, of course, results in a less than perfect combustion and increased emissions and reduced efficiency at low RPMs. This means that depending on the engine and fuel system design, in some cases a port-injected engine may have less emissions and better efficiency than a direct-injected engine at low RPMs. Another problem that direct injection faces is supplying enough fuel at high RPMs. Let's imagine an engine running at 6,500 RPM. At 6.5 rotations per minute, one single engine rotation or revolution lasts only 9 milliseconds, which means that one single engine stroke is 4.5 milliseconds. And as we said, most recent direct injection setups only start injecting in the second half of the compression stroke, which means that there's only 2.25 milliseconds of time available to inject all the fuel that's needed. To put this into perspective, the average human blink is 100 to 150 milliseconds. Now, even if we were to somehow start injecting at the very beginning of the intake stroke, which never happens, this gives us only 18 milliseconds to inject the fuel before combustion actually starts. Now, port injection doesn't have to worry about the start of the combustion event because the injector sits behind the intake valve, which is closed during the combustion stroke and at all other strokes except the intake stroke, which means that it's keeping the injectors away from the combustion. In other words, in the case of port injection, we can start injecting during the compression stroke and keep injecting throughout the combustion and the exhaust stroke all the way until the next intake stroke when the intake valves open again. The fuel will simply accumulate behind the intake valves and enter all at once when the valves open again. This means that if you install injectors with sufficient capacity inside a port-injected engine, you will never run out of fuel. In other words, you can rev as high as your internals can survive. The port injection setup will never be an obstruction to your RPM limit. But that's not the case with direct injection, because as RPMs increase, the time frame for injection becomes so small that no amount of injector capacity or fuel pressure can make up for it. And this is why, on average, direct injection only engines are limited to about 6,500 RPM. There are exceptions with higher RPM limits that are achieved at the expense of emissions or efficiency, but the common RPM limit is usually around 6,500 RPM or less. Now, the location of injection carries one final benefit in favor of port injection. Now, gasoline is a great solvent. Want to clean an old, greasy, gunky part? Just get some gasoline and a brush and watch magic happens. And as we said, the backs of the intake valves in a port-injected engine are constantly exposed to this stream of gasoline coming from the injectors, which means that they can never get dirty. They're constantly being cleaned. Of course, this is not the case in direct injection engines because the injector is inside the combustion chamber, and thus it never sprays fuel on the back of the intake valves, which means that all sorts of carbon deposits, gunk and other junk from the vehicle's PCV system can accumulate on the back of the intake valves in direct injection only engines. Now, over time, these deposits can pile up so much on the backs of the valves that they lead to a distorted and reduced cross-section of the intake port, which means that less air can come into the engine, which of course reduces performance and or leads to a rough-running engine. Now, there are ways to try and prevent these deposits using oil catch cans or fuel additives, but results are mixed, and the need to eventually mechanically clean the backs of the valves is simply inevitable, and it usually happens when the engine has around 100 to 150,000 kilometers on it. Now, this is of course a time-consuming and expensive job, which sometimes even requires the complete removal of the cylinder head to access the valves and clean everything. Of course, this leads to increased maintenance costs for direct injection engines, something that many see as the main drawback of these engines. Another potential issue with direct injection only engines, especially earlier models of these engines, is that the constant introduction of fresh, sometimes poorly vaporized fuel would actually dilute or wash away the protective layer of oil on the cylinder walls. This of course would lead to increased wear and tear and reduced engine longevity. However, newer models have overcome this issue by changing the direction of the injection away from the cylinder walls, which means that most newer direct injection only engines don't really suffer from this issue. Another problem that the deposits on the backs of the valves can contribute to is LSPI, or low speed pre-ignition. Now, as we said, knock is abnormal combustion that occurs after the spark plug is fired. Pre-ignition is abnormal combustion that occurs before the spark plug is fired, and pre-ignition is in most cases worse and more damaging than knock because the piston is moving into the abnormal combustion instead of running away from it, as in the case of knock. Now, low speed pre-ignition occurs during low speed and the high engine load scenarios. As we said, during low engine RPM, low engine speeds, the pistons in direct injection only engines have trouble tumbling and mixing the air-fuel mixture because the piston moves slowly, leading to pockets of unburned fuel floating around in the air-fuel mixture. At the same time, a high load scenario means that the ECU will instruct the injectors to inject more fuel. So in other words, you need to floor it from a low RPM in a direct injection only engine to create the preconditions needed for LSPI. Now, the other thing that needs to happen is that a particle from the back of the valves needs to fall off and enter the chamber, or maybe an oil droplet makes it past the piston rings and enters the chamber. Then this oil droplet and or particle can mix with the unmixed fuel floating around in the air-fuel mixture, and then this newly formed combo will get exposed to the very high compression ratio of the direct injection only engine, and boom, the combination gets self-ignited before the spark plug fires, leading to pre-ignition. The results are often catastrophic, and if pre-ignition keeps occurring and is left untreated, the engine will likely receive catastrophic damage and will need a full rebuild. Of course, high mileage engines are more prone to this because they will have more deposits on the back of the intake valves, and also they will have more wear and tear on the cylinders and the piston rings, making it easier for an oil droplet to make it into the chamber. So here we have an overview of both port and direct injection. And as we can conclude, neither setup is really ideal. Direct injection can improve performance, reduce fuel consumption and improve emissions, but at the cost of increased maintenance and some potential problems. So faced with the drawbacks of both setups and a need to keep meeting efficiency and emission standards, car manufacturers have decided to combine direct and port injection into a single setup, thus creating dual injection. Interestingly enough, combining the two types of injection stacks up the benefits but gets rid of the drawback. The only expense is an increased number of moving parts and increased production costs, because now instead of only one injector, each cylinder has to have two injectors, both a direct injector and a port injector. So how does dual injection work? Well, if you watch this video, you can probably already guess. At whole engine RPM, we're going to rely on the good fuel vaporization and air-fuel homogenization properties of port injection, which means good combustion and reduced emissions at all RPMs. It also means that we're spraying fuel at the backs of the inlet valves, which means no deposits, no increased maintenance costs, and reduced potential for low-speed pre-ignition. As RPMs and piston speeds increase, direct injection steps in. The high piston speeds means good air-fuel mixing, and the super accurate nature of direct injection means that we can increase the compression ratio of the engine, leading to improved performance and efficiency, while at the same time reducing emissions and fuel consumption at higher engine speeds. Want to rev high and keep making power at high RPMs? No problem. When direct injection runs out of time to do its thing, the ECU can simply instruct the port injectors to rejoin the game at maximum engine loads near the RPM limit. They're going to supply the extra fuel that direct injection doesn't have the time to supply, and voila, all the fuel you need at any RPM. And also all the benefits and none of the drawbacks. The reason why more and more manufacturers are packing dual injection into their engines. And there you have it, something that I hope is a comprehensive overview of the three different kinds of gasoline injection technologies. I hope you enjoyed watching this video, and I hope you learned something in the process, or maybe answered a question you might have had about this topic. As always, thanks a lot for watching. I'll be seeing you soon with more fun and useful stuff on the D4H.